Okay, this is active filter design, lecture 32. In the last class, we were discussing the differential pair and what one might do to increase the output impedance of the differential pair. And then we said the finite DC gain of the transconductor is caused by the finite output impedance of the NMOS devices and the PMOS current sources. The PMOS current sources, unfortunately, do not add any signal, but are just presenting a finite output impedance. So, in order to enhance the DC gain of the transconductor, what would one would do would be to choose better current sources, which in this case amounts to so-called cascoding of the original current sources. This goes to some bias voltage VB2 and this goes to CMFB, where CMFB is derived from the common mode feedback loop. Yes, at the back, what is happening? Okay, this is VCM plus VD, VCM minus VD. All right. Now, what we were looking at the tail end of the last class was to figure out what effect the cascode has on the noise performance. Okay, and we'll do that for an NMOS cascode because you're more familiar, hopefully, with the NMOS than with PMOS devices. The same reasoning will apply for PMOS transistors. So, in other words, earlier that is when we didn't have the cascode, this was connected to some bias voltage VB1. This is the current source. This current is I in the sense that VB1 is chosen such that the drain current is I and VB1 is generated by a mirror and so on. And now we have a cascode where you not only have the lower device. What must this potential be? If I want to have the same current, what should the potential there be? It must be also VB1 and this voltage must be VB2 and what is the absolute minimum voltage that VB2 can be? VT plus 2 times delta V. Okay. All right. And what is the absolute lowest potential that you must have across this current source in order for this to behave like a current source? 2 delta V. Very good. Okay. Now, as we all know, transistors not only have the quiescent current but also have noise. In other words, this is 8 kT by 3 gm is the spectral density of this noise current source. Let me call this I1. Okay. Now, what would be the corresponding situation in the cascoded current source? If I want to find, in this situation here, apart from the current of I get a zero mean current, noise current, whose spectral density is 8 kT by 3 gm ampere square per hertz, right. Now, I would like to find what the, it's understood that given that there are two transistors, each of these transistors is noisy, it therefore follows that even for the cascoded current source, the current drawn will be some I plus some noise. We are trying to figure out what that noise is and how that compares with, how the strength of that noise source compares with 8 kT by 3 gm. Is this clear? Okay. So, if this is I, what is the, how would I find the spectral density of the noise coming out? So, I replace every transistor with its equivalent noise source, which is I1 and what else? I2 from where to where? From the drain to source. It's not from drain to ground. Okay, this must be I2. Okay, and I'd like to find, this is I plus let me call this I, small I sub out. Okay, it is clear. So to find I out in terms of I1 and I2, what will I do? How would I figure out I out in terms of I1 and I2? People, come on. Okay, first we assume that both these sources are deterministic. Find the transfer function from I1 to I out and I2 to I out, and then add their spectral densities, because I1 and I2 will be uncorrelated. Okay, so what do you think the easiest way of doing this is to use superposition, right? So what is the transfer function from I1 to I out? So I1, so I out must be I1 plus something into I2. Under what circumstances is the transfer function from I1 to I out equal to 1? Yes, okay. So please note that as far as this current source is concerned, right, it sees two impedances. One is the input impedance of the common gate device above. The other impedance is the RDS or the GDS of the lower transistor. This current will simply split in the ratio of those two conductances, right? And almost all of it will go to through the top transistor, simply because the input impedance looking there is 1 over GM, whereas the impedance looking below is RO, and we know that for a transistor operating in saturation, GM-RO is a large number, correct? Which means that the looking in impedance of the current control currents of the common gate transistor will be much lower than that the output impedance of the lower transistor, which means that we can say that I out is approximately I1, right? That order of the constant multiplying I1 will be of the form GM-RO by GM-RO plus 1, right, which will be very close to unity, okay, plus some other gain into I2. Okay. Now, how do we find the gain from I2 to I out? Let me draw this diagram in a less cluttered fashion. So we have finished dealing with I1. So this is VB1, VB2. Now we are interested in finding the transfer function from I2 to I out. So how do you think we could do this? Okay, so those of you who know the trick, right? You could actually do the math. It's a bit messy. So we split this. I mean, I find the transfer function from so if this is Ix and this is Iy, what is I out in terms of Ix and Iy? You can do this again by superposition, right? Assume Ix is not there. What is the transfer function from Ii to I out? It is simply Iy. Okay, if Iy was not there and it's only Ix, minus Ix. Okay. Now, if Iy was equal to Ix, I out would be right? So if Iy was the same as Ix, then I could simply replace that separate connection. I could connect them together because Ix is the same as Iy, right? And if you have two identical current sources in series, then I can replace them by a single current source. So in other words, if I had Iy like this, what would be I out? Would simply be 0. Does that make sense? Okay. So in other words, the transfer function from I2 back to this circuit diagram to I out is simply I2 from, okay, so in other words, I out is nothing but I1 times approximately 1 plus 0 times I2.
So this can be proved by the same logic also, like I2 is 2 impedances, so it will not go down, it will go up. So it will, whatever logic you have for I1.
Yes.
Same logic you can have I2 also, it is 2 impedances, one down and one up.
Yeah, sure. Yeah. So what he's pointing out is I2 will see two impedances, more it will all go through the top transistor and will cancel out with the other arm of I2, which is the same thing. Understand? Okay. So the bottom line is, what is the conclusion we draw from this study? What is the noise spectral density of I out in the cascoded case? Is the same as the spectral density of I1, which is 8 kT by 3 gm. Is this clear? So cascode increases output impedance, right, at the cost of but it's important to note that there is no noise penalty. Is this clear? All right. So this finally therefore is our complete transconductor with whatever improvements we've deemed to be possible. I am not going to draw here the common mode feedback circuit, which you have seen quite extensively. And also, I mean, another thing to bear in mind is that this VB2 and all that will not be available from outside. You have to generate it yourself. And how do you think you'll be able to generate VB2? Let's get back to the NMOS example. This is the cascode right. This is VB2, this is VB1. I need to generate VB2 and VB1. How will I generate VB1? Use a current mirror. In the simplest case, all right, it is this, okay, and assuming all transistors are the same size, what is this absolute potential? Vt plus delta V. Okay, it's good practice to keep using delta V, right? Simply to avoid carrying over a square root 2I by blah 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 mu and C ox W by L. Pardon? No, I am just illustrating this with respect to a general NMOS cascode. Okay, you understand? The same thing will hold for PMOS. The only reason I am not doing PMOS is because you guys are not as familiar as you should be with everything follows from VDD and so on. I thought you guys are generally more familiar with NMOS transistors, and which is why I will discuss this with NMOS. Once you get the idea, It's straightforward to flip everything to make things with PMOS transistors. Okay. So what is VB2? What is the lowest value VB2 can be? We need to generate, let's say, VT plus 2 delta V. So what do you think is the easiest way of generating VT plus 2 delta V?
We can have something with size 1/4.
Okay. So we know that this transistor carries a current I and so does this, and we also know that if a transistor of size X, when I say size X it means some W by L. If a transistor of size X has an overdrive of delta V, right? Okay, you can interpret VT plus 2 delta V as the gate source voltage of a transistor which is carrying 4 times the current, right, but has the same size, or has 1/4 the size and is carrying the same current. Okay, so or some combination of the two. So what one could do, this is I and this is X by 4. All right, this goes this way. You understand? Okay. All right. Now I'll have to add a couple of practical notes here. So often in circuit design, you will end up with, for example, let's say you end up with a W by L equal to 10 by 0.18. Okay. So technically this is a possibility. This is a MOS transistor, which is the gate. The thin long sliver is the gate. Okay, which is the width and which is the length? This is the length, this is the width. All right. Now the question is, do you want to make a transistor 10 by 1? I mean, if you wanted to make a transistor 10 by 0.18, is this a good way of making a transistor of size 10 by 0.18? You understand? Please note that we are interested in matching which all transistors? Okay. All right. See, all our calculations will only make sense if the transistors are matched. Okay. Now the question is this okay? Now think of these two transistors, M1, let me call this M2, and both these transistors have the same gate voltage, have the same, which all nodes are common to M1 and M2? Gate and source. So a conceivable way of laying this out is the following: transistor M1 has the drain and gate shorted, correct? Transistor M2's gate is connected to the gate of transistor M1. Yes, no, yes, okay. And the sources of both the transistors are common and connected to ground. So perhaps okay, this is a reasonable way of doing this. Please note that the red and blue are all metal layers, okay, which serve to connect different terminals of the transistor together. Okay, and which is the output current? So to tap the output current, what I probably would do would be take this wire, and now this wire, if its potential is higher than a certain minimum, will appear like a current sink. Okay. Now the input current pumps into this node. All right. So can somebody comment on, and please note that this current will be exactly the same as I. Okay. Under what all assumptions? Under two assumptions. One, the VDS of both the transistors is exactly identical, and two, most important, VGSs are the same by construction, right? The key point is that they are matched. All right. Only if the two transistors are identical under all respects will the two drain currents be the same, provided after the two transistors being the same, the drain source voltage of M2 is the same as the drain source voltage of M1. Okay. Now, can you comment on if this is a good way? Do you think? Let me mark. So this is the drain, gate, source, gate, drain. So do you think this is a good way of making a mirror, or do you think it's a not so good way of making a mirror? I mean, in principle, this exactly replicates the schematic, right? And we would therefore expect that if this voltage was exactly the same as the VDS of M1, the current that flows through the source must be exactly this current, whatever input current there is. Okay, one good observation is that physically, how does the current flow? From which terminal to which terminal? Current here flows from in this direction, whereas current here flows in pardon? Oh, sorry. Yeah. Electrons flow like this, yes. Okay. The conventional current flows in this direction. And what about in the transistor on the right side? Current flows in this direction. Okay. So, what would you guess? I mean, as engineers, without knowing anything, I mean, it's like saying going from here to central takes the same time as coming from central to here. Is that a good assumption or no? Come on, people. No, this is no great technical skill. I mean, this is just common sense. No, all that is not what I am asking. I am asking question A, give me answer to question B. Huh? No, please understand what I am saying, right? As an engineer, when you look at this and somebody has pointed out this observation, right, that currents are flowing in opposite directions in both the transistors, what would you conclude? If you want to make two things exactly the same, do you think this is a good thing or a bad thing? Yes, no? All right. So we just discussed that these two transistors are not identical. One, because current doesn't flow in the same direction in both the devices, and two, because of this ion implantation process, the way ions are implanted, the shadowing and so on, and therefore the two transistors are technically not identical, though on the schematic you draw them as two identical devices. Okay. So to fix the problem, one could say, okay, we lay out the transistors like this, right, where this is DGS, okay, but this has the problem of unwieldy aspect ratio, because if W by L is much larger than 1, this being W and this being L, all right, this transistor will be skinny and tall, and that's no good. Okay. So the solution is therefore to use for example, let's say you want to realize 10 by 0.18, and if you don't like the aspect ratio, you can realize it as two transistors in parallel, right, and the gates of the transistors are identical. Okay. So now if you wanted to match the two transistors, let's say this was M1, this was M2. Okay. Now, which is the source of M1? Let's say this was the drain, this was the source, this was the drain. Okay. And copy paste source drain. Here please note that we have still made the mistake of these two halves are not identical because current travels in opposite directions, but now both the transistors have the same problem in M2 also. Therefore, this character matches this character, this guy matches this. You understand, right? So the same thing will happen. So this is what is called finger based layout, right, and each one of these guys is called a finger, right, and the way you denote this is, even though the W by L of the transistor is 10 by 0.18, it is denoted as 2 into 5 by 0.18, for example, where 2 stands for the number of fingers and 5 by 0.18 stands for the W by L of each finger. You understand? Okay. So, so the advantage of using laying a transistor out as fingers is to have manageable aspect ratios for the W by L. Is that clear? Alright. And if you want to match two transistors, then the fact that current flows in opposite directions in different fingers does not matter, because the same thing is probably happening in the other transistor. Okay. Further, it always happens to make sense to have an even number of fingers. Why does it make sense to have an even number of fingers?
Because then the current will cancel. Like if you have 3 fingers, then 1 and 1 will cancel, but the third will not cancel.
Yeah, okay. So, well, so if you have 3 fingers, for example, you always have the odd man out where current is traveling in some direction, right? Now, if you copy and paste somewhere else, if you are not careful, you will always you can always make a mistake, and the singleton in the pasted version will have could have current flowing in the opposite direction, right? So that's simply an unnecessary source of error which you need to keep track of everywhere. So the simplest thing is to make even number of fingers, right? This way, since everything is a multiple of 2, you know, if you copy and paste, right, you get, you know, as good a matching as you can without having to worry about all these other factors, right? Another aspect of even number of fingers is the following. Here I chose drain, source, drain. I could have in fact chosen source, drain, source, source, drain, source. So can you comment on the difference between the two layout styles, drain, source, drain versus source, drain, source here? Forget the current directions. Can you comment on the source area and the drain area? So in the source, drain in this example, right? Can you comment on the drain area? As you can see visually, the area of the drain is this guy, and that is much smaller than the area of the source by a factor of how much? By a factor of 2. Correct? You understand? So especially in our situation where we are sensitive to parasitics, right? Ideally we want the parasitic capacitance that appears at those nodes to be as small or as large as possible. As small as possible. Why? I mean, all that will add to the integrating capacitance. Correct? So you want that parasitic capacitance to be as small as possible. We have seen why it makes sense to choose even number of fingers. Even after you choose an even number of fingers, there are two possibilities to choose the two possibilities. You can choose the outer islands as the drain or the inner islands as the drain, right? Which makes sense here? Which makes sense, red or blue? Source, drain, source, or drain, source, drain? Source, drain, source, because anyway we are not really interested in the source of this transistor, correct? Because that's not appearing in the signal path. We are only interested in the drain, correct? And we want the drain capacitance to be as small as possible. The drain capacitance is proportional to the area occupied by the drain. So choosing an even number of fingers and choosing this style, right? where the drain is shared between the fingers, okay, results in the least possible parasitic capacitance. Does it make sense? Okay, which is why so this finger type design is also what is commonly indicated on schematics, right? So, for example, assuming the transistor of infinite output impedance, right? Let's say this is 10 by 0.18 and this is 2 into 5 by 0.18. What is this current? Do you think it will be exactly I, or it will be different? What is this? What is the meaning of 10 by 0.18? It's a single finger of 10 by 0.18, whereas this is 2 fingers of 5 by 0.18. So what does that mean? I mean, are 2 fingers of 5 by 0.18 exactly equal to 1 finger of 10 by 0.18? They will not be. Okay, all right. So whenever you want exact matching, you should never commit this error, right? So you should only have a fixed finger size, and to get ratios of currents, you only change the number of fingers. Don't mess around with the size of each finger. Is this clear? Okay. There is also another reason why a 10 by 0.18 device is not the same as 2 5 by 0.18 devices, right? Because it turns out that the actual W, the electrical width of the transistor, is not the same as the physical width. There will be some undercut, there will be all sorts of stuff. So in this case, it will be W minus 2 delta W is the actual electrical width of the transistor, which you need to plug into the expression. So this will be W minus 2 delta W by L. This transistor will be W by 2, which is the geometrical length width of the transistor, minus 2 delta W, because that undercut remains fixed, okay, divided by L, and this remains the same. So this transistor is equivalent to 2 times W by 2 minus 2 W by L. So clearly we see that the aspect ratio is not the same, though they are approximately the same as long as delta W is much smaller than W. Correct? So if you are interested in replicating current properly, what will you do? You have the same W by L for all the fingers and get various currents only by changing the number of fingers. You understand? So you will find in most schema, and the moment you find on a schematic something like this, you know that it's not been thought out properly, because you should never have odd numbered fingers. You understand? Always stick to fingers and 2 even number of fingers, right? And 3, if the parasitic at the source is important, then you will choose, you will share the sources. If the parasitic at the drain is important, you will share the drains. It's common sense. That's all. Once you know this, depending on the situation of the circuit, you know if the source parasitic is important, the drain parasitic is important, and choose appropriate. Does it make sense?
What if we need an odd ratio?
Pardon? Yeah, go ahead.
Say something like ratio of 3.
Okay, so if you need a weird ratio, for example, let's say you want 3 is actually it's completely harmless. So let's say this was 2 into W by L. If I want 3i, what will I do? I will I mean, equivalently, I will copy and paste 3 times. So this will be 2 into W by L, 2 into W by L, and 2 times W by L, which is basically 6 into W by L. You understand? Now, if somebody says I want 3.14, then what would you do? You just say, I don't want 3.14. That's all. Okay. So you shouldn't have all such. In principle, you shouldn't have all such weird numbers. Okay. You understand? If you absolutely have to have it, then you have to find the the closest rational number and do all this messy stuff. Okay. But all these antics are best avoided. Just always in engineering, remember one thing. Keep it simple, right? So as simple as possible. If things don't work, then either change the spec or find some other way out. Okay. The more complicated something gets, the less the probability of success. You understand? Okay. So always solutions which are simple are most likely to work. Okay. So we'll stop here. We'll continue in the next class.